Welcome back. Up to this point, we have studied the growth of reference functions. As a side note, you're supposed to remember the table that I included here, but I'm going to include it in here in my slides for a little while longer until you completely memorize it. Now remember also that it is possible to build new functions by combining existing functions, for example, by adding them together. So in this segment, we're going to study the growth of such functions, functions that are obtained by addition of existing functions. So let's state our first theorem, number 1. Let's say you have two functions, f1 of n and f2 of n. And let's say that f1 of n is big O of g1 of n, and f2 of n is big O of g2 of n. What can you tell about the new function f1 plus f2 of n in terms of big O upper bounds? Well, since f1 is upper bounded by g1 and f2 is upper bounded by g2, it's pretty easy to prove that the function f1 plus f2 is upper bounded by the maximum function between g1 and g2, meaning by the function that is, or that has the largest rate of growth among g1 and g2. So that is our first theorem, and before applying it to some examples, let's look at a corollary of this theorem. This corollary is going to have two parts. Part A states that if the function f1 of n is big O of g of n, and the function f2 of n is also big O of g of n, then the sum of these two functions, f1 plus f2, is also big O of g of n. Now the reason this theorem is a corollary of the first one is because it's an obvious consequence of it. Consider, for example, that this assumption here matches exactly this one, except we call the function g of n instead of g1 of n, and this assumption here also matches this one, where g2 of n is called g of n. So this is a special case of this theorem where both f1 and f2 are big O of the same function, namely g of n, so there's no need to distinguish them here. So if g1 and g2 are the same function, what is the maximum of those two functions? Well, it's just g of n. So therefore, it follows immediately that the sum of f1 and f2 is big O of g of n. Now, part B of the corollary states that if f of n is big O of g of n, then the function f plus g of n is also big O of g of n. Now realize that we have the addition of two functions here, where f of n is assumed to be big O of g of n. So consider the situation where f of n is big O of g of n, and of course, g of n is also big O of g of n. So therefore, when you add up f and g, the resulting function is big O of the maximum of g of n and g of n, which is, again, g of n. So what this part of the corollary is saying is that if f of n is upper bounded by g of n, then the sum of f and its upper bound is also upper bounded by the upper bound function itself. Now let's use these theorems to answer a few true-false questions. The first one states that the function f of n equals 17 times log n plus 13 is big O of n. So we recognize here that the function f of n is the sum of two other functions, namely f1 of n and f2 of n. So we're going to consider each one of these functions in turn. f1 of n is a constant times the logarithmic function. Since the logarithmic function is big O of log n, and we're multiplying by a constant, f1 of n is also big O of log n. That's the first partial result. Now let's look at the second function, 13. That's a constant function, so that function is big O of 1. That's the second partial result. Now what happens when we add a function that's big O of log n to a function that's big O of 1? Well, the theorem states that the resulting function is big O of the largest of those two functions. So now we can use the table, or you should remember that big O of log n grows faster than big O of 1. Therefore, the sum of these two functions is big O of log n. Now we can use the table a second time, or again you should really remember that the linear function f of n equals n grows faster than the function log n. Therefore, if this function is big O of log n, it's also big O of n. So the answer to this question is true. Now the second true-false question we will consider is the following. Is the function f of n equals n squared plus 33n minus 4 big O of n log n? You should immediately recognize this function as a polynomial function of degree 2. From a previous theorem, we know that this function is upper bounded by n squared. In fact, it's pretty easy to prove that because n squared grows faster than n log n, this function is not upper bounded by n log n. So the answer to this question is false. The way you would prove this is, say, by doing a proof by contradiction and showing that when n gets large enough, there is no way that this function could be upper bounded by n log n. Again, we're using the fact here that you should remember, namely that n squared grows faster than n log n. For our next true-false question, consider the function f of n equals 8 times n plus 5. Is this function big O of n to the power 3/2? You should immediately recognize this function as a polynomial of degree 1. We know this function is big O of n, and since n to the power 3/2 grows faster than n, then clearly this function is big O of n to the power 3/2. Now, why is n to the power 3/2 going faster than n? It's simply because that number, that function of n, is equal to n power 1 times n power 1/2. Since 1 plus 1/2 is 2/2 plus 1/2, or 3/2. Now, this function, n power 1/2, which is also the square root of n, clearly grows faster than the constant function 1. And therefore, this product clearly grows faster than n. Again, in conclusion, since this function is big O of n, and this function grows faster than n, then this polynomial function is big O of n to the power 3/2. For our last example, consider this true-false question. Is the function f of n equals 2 to the power n plus n to the power 100 big O of 3 to the power n? We recognize this function as the addition of two other functions, so let's consider the first one, 2 to the power n. That is the exponential function to the base 2, and the second function is the polynomial function, the polynomial of degree 100. Now, you should remember, again, you can refer to the table here for now, that any exponential function to any base greater than 1 grows faster than any polynomial function of any degree. So according to the theorem, since this function is big O of 2 to the n, this function is big O of n to the power 100, and this function goes much faster than the other one, their sum is big O of 2 to the power n. Now, 3 to the power n grows faster than 2 to the power n since it's also an exponential function with a larger base. Therefore, this function is not only big O of 2 to the power n, it's also big O of 3 to the power n, and therefore the answer to this question is true.